Okay, now that we've seen limits and now that we've also seen what can go wrong with limits, we're going to talk about the kinds of functions for which limits really work very well, and those things are called continuous functions. That will lead one more time to a quick analysis as to what can go wrong with limits, and in the next presentation we'll talk about some of the properties of continuous functions. So let's get to it. What's continuity? Well, let's see. Some limits can be computed by plugging in the number. And if you're looking at what we have done in our limit computations so far, the goal typically was to cancel that 0 in the denominator so that we could compute the limit by plugging in the number. In this presentation, we'll introduce the functions for which this can be done. And in the next presentation, as I mentioned, we'll talk about some graphical properties, in particular the intermediate value theorem, which is a very important graphical property of these functions. We'll also analyze what can go wrong with limits one more time, and that will ultimately show that the only ways in which limits cannot be computed by plugging in are that there could be a hole, there could be a vertical asymptote, a division by 0, it could be that the left and right branches don't meet, meaning there's a jump. That's the kind of thing that often happens in piecewise defined functions. And one more possibility, the one that we also already glossed over a little bit in the previous presentations, and that is those really bad oscillations. Okay, so what are continuous functions? If f is a function, then f is called continuous at a, at the point a, if and only if the following three conditions are satisfied. First of all, f of a has to be defined. Second of all, the limit as x goes to a of the function must exist. And third, the limit as x goes to a of f of x must be equal to f of a. That is typically, or very often, remembered by just people remembering the third one. Basically, you can do that, but you've got to remember, if for this equation to make sense, f of a must be defined and the limit must exist. Otherwise, that equation doesn't make sense. If a function is continuous at every point in a set, then f is called continuous on that set. And if f is continuous on the real numbers, we'll simply say that f is continuous. Points where the function is not continuous are called discontinuities. And the function is, well, discontinuous there. So we're not going to talk about function being not continuous. The common language is to talk about discontinuities and functions being discontinuous. Now, that's a bunch of vocabulary. We've seen that before, but is there graphical meaning in it? And well, there is. Basically, the idea is that continuous functions can be drawn in one pencil stroke. If a function is continuous on the real line, well, then basically the f of a being defined means that no matter what we do, the pencil can always go somewhere as we draw the function. Second of all, the existence of the limit means that whatever point we approach, the pencil approaches in an orderly fashion, and that means we don't have to stop to incorporate a jump, a vertical asymptote, or some kind of an infinite oscillation. And third of all, well, the approach and the target must meet, so that excludes the jumps, right? The orderly approach could still have a jump possibility, but once we've got that approach, oh no, the orderly approach can have a assures that there is no jump. Approach and target meeting just means that the point doesn't actually jump out of the function. We'll see an example of that in just a second. Okay, so let's take a look at the following example, and we want to determine where the function is continuous, and we want to justify the answer with the definition of continuity. Well, let's see what goes wrong here. The function is not defined, right? Okay, and that's right, f of -4 is not defined. Then here, the limit does not exist. The limit as x goes to -1 f of x does not exist. Here we have another one where the limit doesn't exist. And here this infinite oscillation also means that the limit does not exist as we approach x, as x approaches 4.5. So that's how you would justify things with the definition of continuity. You wouldn't talk about jump or a hole or anything like that. You have to connect it to the abstract situation. Okay, now abstract examples of continuous functions include that constant functions are continuous, the identity is continuous, and if two functions are continuous, then their sum, difference, and product are continuous. So is the quotient on the domain. We have to make sure that we rule out divisions by 0. And if two functions are continuous, then their composition is continuous too. The number 3 implies that polynomials are continuous. Once we look at quotients, we realize that rational functions are continuous wherever they're defined. The sine and cosine function are continuous. Just think of the graph. It can be drawn in one pencil stroke. The tangent function is continuous on its domain. It's a quotient of continuous functions, but remember it blows up every so often at x equals pi over 2 plus k pi. That's where the zeros of the denominator are. Inverses of continuous functions are continuous. That's actually a pretty sophisticated theorem. Graphically speaking, if you can draw a graph in one pencil stroke, then when you flip that across y equals x, you should still be able to draw that in one pencil stroke. The inverse trigonometric functions are continuous on their domains. Same story. The natural exponential function is continuous. Well, it just goes up very rapidly, right? And the logarithm, being the inverse of the natural exponential function, is also continuous on its domain. So this is very good news, because it means that an awful lot of functions that we're interested in really are continuous in the places where we would expect the function to be continuous. And so now if we're looking at a concrete example where we want to determine where the function x squared plus 2x minus 3 over x minus 1 is continuous, well, the only thing that could go wrong here is that the limit doesn't exist because of a division by 0. So we set the denominator equal to 0, we end up with x equals 1, and that means the function is continuous everywhere except at 1. But at the same time, on the other hand, if we're looking at the limit as x goes to 1 of this function, well, and here's where I actually solved it with factoring, right? X squared plus 2x minus 3 is x plus 1 times x plus 3 over x minus 1. Cancel the x minus 1s, you end up with the limit of x plus 3, that's 4. Well, if the limit exists, it ought to be possible to somehow fill that in and just redefine the function and make it continuous, and that's where we're headed next. Because if we're looking at this function, the only problem with this function is that there's a hole. And that's also reflected in the data table. Now, if we extend this function, and if a function is not defined at a point, well, then we can just go ahead and define it there. And if we define that wrong, well, duh, if we just toss the point down here, well, then the data table shows that the extension is not continuous. But we don't need to pretend we don't know where the point should go. The point should, of course, go right here. And so if we were to redefine the function to be 4 at 1, then also the data table would show that the function ought to be continuous. And so that means with this continuous extension, as it's called, we can even toss that point out, and we realize that with the continuous extension, this function really is just equal to f of x equals x plus 3. And yeah, so that was one thing. And well, we also want to work with parameters and we also want to work with piecewise defined functions. And well, for a piecewise defined function, continuity typically is only in doubt where the definition changes. And so we want to know here if this function is continuous at a equals 3. In order to do that, we realize, first of all, it's defined at 3, because f of 3 is -1. The left limit exists, right? That should be the limit as h goes to 0 from above f of 3 minus h. So we're to the left of 3. That would be 2 plus 2 minus 3 minus h. So that's -1 as a limit. And when we approach 3 from the right, well, then the function is 10 minus x squared. So we get the limit h goes to 0 from above 3 plus h, which is the limit h goes to 0 from above of 10 minus 3 plus h squared. That's 10 minus 9, that's 1. And that's not equal to -1, and that means that f is not continuous at a equals 3. And graphically speaking, well, the function comes in from the left as a straight line, and it hits -1 in a what looks like a continuous fashion, but then the function continues here at +1, and because of this jump, the function is not continuous. Note that the parabola is so steep here that this, even though this looks like a straight line, this actually has a little bit of curvature to it here. Okay, now let's work with parameters. Again, because of course parameters prepare us for more sophisticated work, but here also this is some kind of standard problem actually that you sometimes see when you talk about continuity. It's the same function as before, only now we don't have a 2, we've got a c here, and we want to know how to adjust this left branch to make the function continuous at a equals 3. Okay, well, f of 3 is still c minus 3, which is just c minus 3. The left limit is the limit as h goes to 0 from above of f of 3 minus h, so that's c minus 3 minus h, which ends up being c minus 3. And the limit as x approaches 3 from the right of the function, that's the function of the limit of f of 3 plus h, where h is positive, and that would be the limit of 10 minus 3 plus h squared, and that would be 9 minus, that would be 9, yeah. 9, 1, sure. 10 minus 9 plus a bunch of stuff that's multiplied by h, so that's 10 minus 9, that's 1. Okay, and now what we need is, of course, that the left branch and the right branch are equal. So we set 1 equal to c minus 3, and that gives us c minus 3 equals 1, c equals 4. And so fc, because this is a family of functions, if you will, that's continuous at a equals 3 exactly for c equals 4. And f4 of x is 4 minus x for x smaller or equal than 3, and 10 minus x squared for x greater than 3. And, well, what does it look like? Basically what we've done is we've taken the function that we had before, and we've adjusted the value of c in such a way that now things actually link up, and for c equals 4, that actually does happen. And so now here for c equals 4, we have the right thing. But basically what we've done is we've just adjusted the parameters so that things do work out. And then, of course, again, we don't need to emphasize this point, and we can simply see here that this, even though this function has a corner here, corners are allowed for continuous function, this thing ends up being continuous. All right, I hiccuped a little bit after we did that removal of the discontinuity for the function that ended up being just equal to x plus 3, and that's because I wanted to talk about the 4 kinds of discontinuities. Well, we'll do that now. Basically, if the limit exists but is not equal to the value of the function at the point, or if the function is just not defined there, we speak of a removable discontinuity. And that is because even though formally we have a discontinuity here, if we fill it in, and that can be because the function is undefined or because the point is just chosen awkwardly, if we just go ahead and put that point from down here up here, then the discontinuity would be removed and we'd end up with a continuous function. So that makes a good bit of sense. If the left limit and the right limit exist, but they're not equal, we speak of a jump discontinuity. That basically means that the left branch and the right branch don't meet. And that's what a jump is, sure. It's also happening with stuff that's not necessarily horizontal. If at least one of the both limits is infinite, or if f is unbounded on any interval that contains a, we speak of an infinite discontinuity, and that's these kinds of singularities that give you vertical asymptotes. Sorry for overlapping the text here, but basically I'm trying to model this visualization thing that I've talked about before, and that is, as you see the words, you also want to see the right kind of picture in your mind. Now, I can't project it into your mind, but I can project a few things on the screen, and that's what we're doing here. Okay, so continue the list. Finally, if the function is bounded in a small interval around a, and if at least one of those limits does not exist, well, then the only way that the limit can't exist when the function is bounded is by the function oscillating like crazy, and that's what happens to a function like sine 1 over x. That's the picture here. That's got infinitely many oscillations of positive amplitude that stays positive as we approach 0 in the interval from negative 0.2 to 0.2, and so there is no way we're going to get orderly behavior near the origin, so that thing doesn't have a limit at 0. And remember, the discontinuity by oscillation, that's the one that really is typically discussed mostly in more advanced classes, but the picture is just, it acts like sine of 1 over x near the origin. Okay, so in conclusion, we can look at an example one more time and just classify the discontinuities of a given function and just practice the terminology a little bit. So here's that function we've looked at several times now. The first discontinuity is removable. If we just fill in this dot, we end up with something that's continuous. The next discontinuity is infinite. We've got a vertical asymptote. That discontinuity here is a jump because the left limit and the right limit aren't equal. And finally, we have a discontinuity by oscillation. Remember, those things are not discussed that often in calculus, but nonetheless, it can't hurt to know about these things. All right, well, That's what we need to know about continuous functions. And you could say that this is, again, mathematics for the sake of mathematics, but it turns out that the property of continuity has some very nice abstract consequences that lead to the development of numerical methods such as the bisection method, and that's what we're going to discuss in the next presentation. I'll see you there.